Jai students, welcome to my YouTube channel. Students, take up one idea. Make that one idea your life. Think of it. Dream of it. Live on that idea. Let your muscles, your brain, your nerves, your every part of body be full of that idea. And just leave every other idea alone. This is the only way to success. This was the sayings of our great Swami Vivekananda ji. So students, in order to achieve success, you need to follow that one idea which is close to your heart. So with that students, let's begin today's session. Today we are going to discuss magnetic elements of Earth. In the previous lecture, we have discussed some technical terms like geographical axis, then geographical poles, equator, geographical meridian, then magnetic axis, magnetic poles, magnetic meridian, magnetic equator, isn't it? So in case you want to fall back on that lecture, I will provide a link of that lecture, previous lecture, in my description section, right? So please go through that video and then only you will be truly able to understand today's topic, which is magnetic elements of Earth. So students, magnetic elements of Earth. These are basically the physical quantities. These are actually three physical quantities which we require to describe the Earth's magnetic field completely. Earth's magnetic field completely means both in magnitude as well as direction. So what are magnetic elements of Earth? These are the quantities which we use to describe the Earth's magnetic field completely. Right? And there are three magnetic elements of Earth. The first one is magnetic declination. The second one is magnetic inclination. It is also known as angle of depth. And the third one is, students, the horizontal component of Earth's magnetic field. Right? So before we start discussing it, let us recap some important terms and definitions, right? So students, you all are aware, suppose this is the Earth. For all practical considerations, we can assume the Earth to be perfectly spherical. So this is the imaginary line about which the Earth rotates. And it rotates, its sense of rotation, as we are aware, it's from west to east, that is in the anti-clockwise direction, isn't it? So, it rotates about its axis with an angular speed of 2 pi by t, where capital T is the time period, and the time period for the Earth to complete one rotation is about 24 hours. So, this imaginary line about which the Earth rotates from west to east, that is in the anti-clockwise direction, is known as Geographic Axis. And students, we are aware of Earth's magnetic field, isn't it? And as per William Gilbert, he suggested that Earth's magnetic field can be assumed or considered to be due to a huge bar magnet lying inside the core of the Earth. There is no such huge magnet inside the core, but it's just an assumption. So, this is the axis of that bar magnet, which is assumed to be present inside the Earth's core. The axis of this bar magnet, which is assumed to be inside the core of the Earth, that is known as magnetic axis. And we have discussed, students, this must be the south and this is north. So this is magnetic south pole and this will be the magnetic north pole of the Earth. And this line, as I stated earlier, this is the axis about which the Earth rotates. So this is geographical north and it will be geographical south. Now when a bar magnet is suspended freely, then what happens? It will experience a torque under the influence of Earth's magnetic field, and under the influence of Earth's field, it will align itself along the direction of the Earth's field. So students, what I mean to say is that whenever a bar magnet is suspended freely, then it will align itself in the magnetic meridian. Magnetic meridian is an imaginary vertical plane which passes through the magnetic axis. Understood, students? Right? So, let's discuss the first topic, that is magnetic declination. stated the three physical quantities which are required to describe the Earth's magnetic field completely at a place are known as magnetic elements of Earth. The first one is magnetic declination, right? We are aware of the definition of magnetic meridian and geographical meridian. Geographical meridian is an imaginary vertical plane which passes through the geographic axis, and magnetic meridian is the imaginary vertical plane that passes through the magnetic axis, isn't it? The angle between these two planes is known as magnetic declination. So it is defined as the angle between magnetic meridian and geographic meridian. This is the definition of magnetic declination. And we will denote magnetic declination by theta. So how to define magnetic declination? Magnetic declination at a place is defined as the angle between the magnetic meridian and the geographic meridian. Now, in order to understand this concept, I will make use of a teaching aid, which is a simple sponge ball. This is a simple sponge ball, right? So this green arrows, the line whose ends are covered with the green arrows. This is the line I am talking about, the green one. This can be considered to be the geographic axis about which the Earth rotates. Earth rotates like this. Earth will rotate in the anti-clockwise direction about this axis. So this axis, this imaginary line about which the Earth rotates, is known as the geographic axis. Clear? Its sense of rotation is from west to east, that is in the anti-clockwise direction, like this. And students, this one, the red one, this is the axis of this huge bar magnet lying deep inside the core. So this is the magnetic axis. This is the magnetic axis. Clear, students? So if this is geographical north, this must be magnetic south. If this is geographical south, this must be magnetic north, as I have indicated in this diagram as well. Right? Now the point is magnetic declination at a place. Suppose, students, look, this is the point. Let us consider this to be Pathankot. This is the point. This is where we reside. This is Pathankot, right? At this place, we need to find out the magnetic declination. So what we'll do is, we will consider a vertical plane passing through this point and the magnetic axis. The red one is the magnetic axis. So this is the line. I am drawing it over here. You can easily see it like this. This is the line drawn. So students, this is suppose a place which is considered to be Pathankot, right? And this is the magnetic axis, the red one. So just if we cut it like this, the plane will contain this point as well as the magnetic axis. So this plane, this vertical plane, will be known as magnetic meridian, right? And this green one, this represents the geographical axis. So if I connect these two like this, now at the same place, Pathankot, if I join these 2 points and cut a plane passing through these 2 points, that is the plane, vertical plane I am talking about, passes through the magnetic axis and contains this point as well. That is the place where we are finding the magnetic declination, right? So this plane which passes through the green arrow, that is the geographic axis, that is known as geographic meridian. And this plane at the same place which passes through the magnetic axis is known as magnetic meridian. The angle between these two, this one, the angle between these two planes, this is theta, which is the magnetic declination. Clear, students? Again I repeat, I have drawn this diagram as well. So let's check it out. This is a plane, suppose which is passing through the magnetic axis. Just now I have convinced you, right? So this is the magnetic meridian. It is the magnetic meridian. Clear, students? And this is the imaginary vertical plane that is passing through the geographical axis. Suppose this is the place which let us assume it to be Pathankot. So what I have stated is, imagine a vertical plane passing through the geographical axis. So this plane will act as, this is point P. This plane will act as, and this is geographical north. This plane will act as geographical meridian. And this is magnetic south. This plane, vertical plane, contains magnetic axis, and this vertical plane contains geographical axis. So the vertical plane containing geographic axis is the geographical meridian, and the vertical plane containing magnetic axis is the magnetic meridian. And this is the angle between these two planes, which is known as angle of declination at that place, right? So here, this is the angle theta. Clear, students? I hope you are convinced now. So the angle at a place between the magnetic meridian and the geographic meridian is known as magnetic declination. Clear? Let us consider some other point over here. So here, what will be the angle? Connect these 2 points and this one. So these are the 2 planes. This will be the magnetic declination. Suppose at point Q. So point is magnetic declination at a place is defined as the angle between the geographic meridian and the magnetic meridian. Magnetic meridian is the vertical plane passing through the magnetic axis. Geographic meridian is the vertical plane passing through the geographic axis. And my dear students, angle of declination at different places would be different. Here, this theta dash obviously would be different from theta. At some places, the magnetic declination can be same as well. At some other places, the magnetic declination may be 0 as well. That also we'll discuss. So basically, magnetic declination at different points will be different. Suppose this is another point R, another place on the earth R. So now magnetic declination would be this one. This is a plane, vertical plane, and this is another vertical plane. Let us assume it to be passing through the geographic axis. So this angle, suppose theta double dash, it will be the magnetic meridian. And the angle between the magnetic meridian and the geographical meridian, theta double dash. So this will be, theta double dash will be the magnetic declination at place R. Clear? I hope you have understood this. There are some other important terms as well. Let's discuss those terms as well. One is Agonic lines. These are the lines on the Earth's surface connecting those points or connecting those places where the magnetic declination is 0. These are the lines. These are the lines joining points or places on the Earth's surface where magnetic declination is 0. So please do remember it. This is the line joining all those places on the Earth's surface where theta is equal to 0. Okay, students. Again, let's consider this example. As I told you, students, this green one, this represents geographic axis. This red one, it represents magnetic axis, right? Now, suppose this is a point over here. There is a place on the Earth's surface, right? And all the 3 are lying on the same line. Look, all the 3 are lying on the same line. This is a place on the Earth's surface, this one. And if you join a line, then the geographic axis, magnetic axis, all will lie on this line, isn't it? So, what will be the magnetic meridian? You will cut a plane like this, vertical plane passing through the magnetic axis. What will be the geographical meridian? Again, a vertical plane passing through the geographic axis. So at this point, the magnetic meridian as well as the geographic meridian will be the same vertical plane. So what's the angle between these two? That will be 0. So at all the points over here, the magnetic declination would be 0. So this line joining those points on the Earth's surface where magnetic declination is 0 is known as Agonic lines. Clear, students? Similarly, let's proceed further. There are some other definitions as well, like isogonic lines. Isogonic lines. Iso means same. So these are the lines joining those points on the Earth's surface having same value of magnetic declination, right? So these are the lines joining points on the Earth's surface having same value of same or constant value of magnetic declination. Clear, students? So here theta at all those places would be same. So these are the two terms which are quite important. Let's recap this thing, right? So magnetic declination at different places on the Earth's surface may be different. It may be same as well. So magnetic declination at a place is defined as the angle between the geographic meridian and the magnetic meridian. And the lines on the Earth's surface joining those points or places where the magnetic declination is 0, they are known as agonic lines. While the lines on the Earth's surface joining those points where the magnetic declination is same, those lines are known as isogonic lines. Clear? So again, I repeat, if this is the geographical meridian which is passing through the geographic axis, this may be considered to be the magnetic meridian. It is a vertical plane assumed to be passing through the magnetic axis. Then this angle between the geographic meridian and the magnetic meridian represents angle of declination at that particular place. Okay, students, now let us discuss the second magnetic element of Earth, which is magnetic inclination. It is also known as angle of dip. So students, basically it is defined as the angle which the Earth's total magnetic field makes with the horizontal, and we will denote angle of dip, say, by del. So let me make use of this particular aid. This is, students, a vertical plane, this red one. This is a vertical plane, this is a vertical plane. Let us assume it to be passing through the magnetic axis. So this vertical plane will act as magnetic meridian. Clear, students? While the other one, this vertical plane, suppose this vertical plane is passing through the geographic axis. So this one will act as geographic meridian, right? So the angle between these two planes, here it will be clear. From the top view, it will be like this. This is the geographic meridian, this is the magnetic meridian, suppose. So the angle between these two is theta, which is magnetic declination, right? So these are the two planes situated like this. Let us assume this red one to be magnetic meridian, the other one, this one, to be the geographic meridian. Now look, students, this is a freely suspended bar magnet. Suppose this is a freely suspended bar magnet. Now look, I have suspended it free. Free suspension means I have told you in the previous lecture as well. This magnet can move in the horizontal plane as well as it can move freely in the vertical plane, right? So what happens is, at this place, if this magnet is suspended freely, then what happens? It will oscillate and then it will tend to align itself along the direction of Earth's magnetic field. So Earth's magnetic field, it will lie in the magnetic meridian. So this compass needle will lie in the magnetic meridian. It won't lie in any other plane. It will lie only in the magnetic meridian. Its length will be parallel to this plane, isn't it? So here at reaching at this particular place, then what happens is this freely suspended magnet will dip depending on the location of that place. It will dip. So this will represent the direction of Earth's total magnetic field. And this Earth's total magnetic field, the angle which this Earth's total magnetic field makes with the horizontal, this one is the horizontal, this is vertical. So the Earth's total magnetic field, the angle which it makes with the horizontal, it will be the angle of dip or angle of inclination. Again I repeat, students, when a magnet is suspended freely suspended means it can oscillate in the horizontal plane as well as it can oscillate in the vertical plane. That is the actual meaning of freely suspended bar magnet, right? So when a bar magnet is suspended freely at a place, right, then what happens? It will tend to align itself along the direction of the Earth's magnetic field. So therefore, it will lie in the magnetic meridian. Again, this is a very, very important point, students. I repeat, a freely suspended bar magnet will lie in the magnetic meridian. Then depending upon the location of the place, either this needle can remain stationed like this, it can remain parallel to the horizontal, or it may dip somewhat. So this is why the angle of inclination is also known as angle of dip. So what happens is, freely suspended magnet, it will first align itself along the direction of the Earth's field, that is, it will lie in the magnetic meridian, and then it will slightly dip depending on the location of that place. And this needle, this freely suspended bar magnet, will represent the Earth's total magnetic field. And the angle which the Earth's total magnetic field makes with the horizontal, that will be known as the angle of dip. So this freely suspended bar magnet, it can remain horizontal or even it can be like this as well. So as a result, it can make an angle of 0 degree with the horizontal, or it can make an angle of 90 degree with the horizontal. So angle of dip may vary from 0 degree to 90 degree. That we will discuss in detail now, right? So students, first regarding the definition, angle of dip or magnetic inclination. Angle of dip or magnetic inclination is defined as the angle which the Earth's total magnetic field, makes with the horizontal, So that's the definition of angle of dip. So as we have considered this plane to be the magnetic meridian and this other plane to be the geographic meridian. Theta is the magnetic declination that we have already discussed. Now, on suspending a bar magnet freely, what happens is it will tend to align itself in the magnetic meridian and then it might dip through certain angle. With respect to the horizontal, it will dip, right? So, suppose this is the needle. This is the bar magnet. This will represent Earth's total magnetic field. Suppose Earth's total magnetic field is represented by B. Capital B represents the Earth's total magnetic field at a place. Now this is horizontal, this is vertical. The angle which the Earth's total magnetic field makes with the horizontal, this is known as the angle of dip. This is horizontal and this is vertical. Right, students? So again I repeat, angle of dip or the magnetic inclination at a place is defined as the angle which the Earth's total magnetic field makes with the horizontal. Point to be noted is that, students, Earth's total magnetic field, it obviously will lie in the magnetic meridian. A freely suspended magnet, it will align itself along the direction of the Earth's magnetic field, so it will also lie in the magnetic meridian. After it aligns itself in the magnetic meridian, the freely suspended magnet dips through some angle with respect to the horizontal, and that angle is known as angle of dip at that place. Clear? So this is how it is defined. Now, dip circle, that's the instrument which is used to measure the angle of dip or magnetic inclination. This is basically a dip circle. It is fitted with a compass needle and it can freely oscillate in the vertical plane. Normal compass needle, that is able to freely oscillate in the horizontal plane, but this oscillates freely in the vertical plane. So it is observed that on placing this dip circle at the equator, it is found that this compass needle becomes parallel to the horizontal. That is, the angle of dip is 0 at equator. While on the other hand, on placing this dip circle at a point on the poles, the magnetic compass needle, it dips through a maximum angle of 90 degree. So their angle of dip is 90 degree. And at some other place, as shown in the diagram, it dips through certain angle with respect to the horizontal. And this angle is known as dip. This is the angle of dip, right? So students, at equator, this I will prove it with the help of a diagram. So basically at equator, the angle of dip is 0 degree, while at the poles, this I am talking about the magnetic equator and magnetic poles, the angle of dip is 90 degree. And at some other place, the angle of dip will vary between 0 degree and 90 degree. As we approach towards the poles, the angle of dip, its value will keep on increasing and eventually it will become maximum at 90 degree. And if we approach towards the magnetic equator, then angle of dip will keep on decreasing and eventually at the equator, the angle of dip is 0 degree. This I will convince with the help of another diagram, right? So, now let me try to convince you regarding these two known facts. How will you justify yourself that angle of dip? How will you prove that angle of dip at the equator is 0 degree? Angle of dip at the poles is 90 degree. So let's try to verify this. For this, students, we need to draw the magnetic field lines due to Earth. Again, let's concentrate on this particular diagram. This is the imaginary line about which the Earth rotates in the anti-clockwise from west to east. So this is known as the geographic axis. And this is a huge bar magnet which is considered to be deep inside the Earth's core. And the axis of this huge bar magnet assumed to be inside the core of the Earth is known as magnetic axis. Isn't it? It is the magnetic axis. So this is the magnetic south of Earth and this is the magnetic north of Earth. So let's draw the magnetic field lines due to the Earth, right? And as we are aware, students, magnetic field lines are in the form of continuous closed loops. They neither have any emanating point nor do they have any terminating point. They are in the continuous closed loops. Inside the body of the magnetic field lines are directed from south to north, like this. Inside the body of the magnet, it's directed from south to north. And outside the body of the magnet, it is directed from north to south. That is how it is in the form of continuous closed loops. So let me draw some magnetic field lines. It will be like this. Clear, students? So inside the body of the magnet is from south to north, and outside it will be from north to south, like this. And let's draw a symmetrical diagram. Outside it will be from north to south, like this. And inside it will be from south to north. These are the magnetic field lines, which are in the form of continuous closed loops. So, magnetic south, the magnetic field lines will appear to enter. Right? Now if we talk about some conceptual question, like in Australia, whether at any place in Australia, like Sydney, whether the magnetic field lines will seem to go into the ground or it will seem to come out of the ground. So for that, you need to know the location of Australia. It is somewhere in the southern hemisphere, isn't it? So in this case, the magnetic field lines will appear to come out of the ground. Clear, students? From Sydney, which is a place at Australia, the magnetic field lines will seem to come out of the ground. While at some other place over here, the magnetic field lines will seem to enter into the ground. So that's a conceptual question. Anyway, these are the magnetic field lines due to the earth, right? Now what to do is, you are aware when we draw magnetic field lines that at any point the direction of magnetic field is given by drawing a tangent at that particular point. Clear, students? So suppose I want to or I wish to find out the magnetic field at this particular point. Suppose, say at this point. So what I do is, this is the horizontal for me. At this point, this will act as the horizontal. Draw a tangent that will act as a horizontal at that point on the Earth's surface, right? This will act as the horizontal. So at this point, the magnetic field will be along this direction. It will be given by drawing a tangent like this. So if I draw this diagram over here, then the diagram would be somewhat like this. This is the horizontal at this place, right? And this is the direction of the Earth's magnetic field. This is the Earth's total magnetic field. This one. It's given by drawing a tangent. This is the horizontal and this is the Earth's total magnetic field. So the angle which the Earth's total magnetic field makes with the horizontal, that is known as angle of dip. Clear, students? And if you resolve this B into two perpendicular components, one along the horizontal, it will be the horizontal component of Earth's magnetic field, and the other along the vertical, it will be the vertical component of the Earth's magnetic field. Isn't it? So here del will have at this place, which is neither at poles nor at equator. At any other place, the value of angle of dip will lie between 0 and 90 degrees. No doubt regarding this. Clear, students? Again, I can convince you. Over here, students, this is the horizontal. This is the horizontal, right? This is the horizontal. And at this point, the magnetic field, the Earth's total magnetic field would be directed like this. Isn't it? So, if you produce it in the backward direction, this is the angle which this Earth's total magnetic field will make with the horizontal. So, at this place, del will be the angle of dip, which will definitely lie between 0 and 90 degrees. I hope you are able to get convinced. Now, students, take a point on the equator, magnetic equator. This is where the magnetic equator is, right? Take a point over here. Here the horizontal would be like this. This is the horizontal. And the magnetic field line is like this. So if you draw a tangent over here, it will be like this. So look, here magnetic field is parallel to the horizontal. If you draw this diagram over here, it will be like this. This is the horizontal. And this is where the Earth's total magnetic field lies. So at this place, which is a place at the equator, the magnetic field, Earth's total magnetic field, is parallel to the ground, parallel to the horizontal. So as a result, the angle which the Earth's total magnetic field makes with the horizontal is 0 degree. So that is why we conclude that at equator del is 0 degree. If you place this device, which is dip circle at equator, then what will happen? This needle will be like this. It will be aligned perfectly horizontally. That is parallel to the ground. So that del would become 0. Clear? So for that matter, angle of dip at the equator is always 0 degree. Now, at the place at the poles, magnetic poles, this is the horizontal. Now at this point, this is the Earth's total magnetic field. This is the Earth's total magnetic field. What is the angle which the Earth's total magnetic field is making with the horizontal? It is 90 degree. There is no horizontal component. The entire component at the poles is the vertical one. So horizontal component is absent at the poles. So here the Earth's total magnetic field is making an angle of 90 degree with the horizontal. And if you place this dip circle over here, then the needle would be like this. This is the magnetic needle, so it will be like this. So it will point like this. It will be totally vertical. So it will make an angle of 90 degree with the horizontal. So angle of dip at the poles is always 90 degree. Clear? And at any other place, the angle of dip will lie between 0 degree and 90 degree. So students, let me again repeat this topic. Angle of dip at a place is defined as the angle which the intensity of Earth's total magnetic field makes with the horizontal. Angle of dip at the equator is 0 degree. Angle of dip at the poles is 90 degree. Angle of dip is also known as magnetic inclination. And there are two technical terms associated with it. One is Aclinic lines. These are the magnetic lines joining points on the Earth's surface where the angle of dip is 0. Angle of dip is 0 at the equator. So basically magnetic equator is known as Aclinic line. Right? Magnetic equator. All those points lying on the magnetic equator, there the angle of dip is 0. And that line is known as Aclinic line. Aclinic line. So Aclinic line means the angle of dip must be 0. So let me write down the definition of Aclinic lines. These are the lines joining places or points on the Earth's surface having 0 angle of dip. Clear, students? Del is equal to 0. And del is 0 only at the equator. So magnetic equator is sometimes known as Aclinic line. Then the other one is Isoclinic. Iso, I have told you, the meaning of iso is same. Isoclinic line. Obviously, these are the lines joining those places or points on the Earth's surface where the angle of dip is constant or same. So lines joining points or places on the Earth's surface where angle of dip is same or constant. Iso means same. So do remember these two definitions, Aclinic lines and isoclinic lines. Right, students? So we have done magnetic declination and magnetic inclination. Now, third one, horizontal component of Earth's magnetic field. So this we have already discussed. It is basically the component of Earth's magnetic field along the horizontal. Nothing new in it. I repeat, students, the component of Earth's total magnetic field along the horizontal is known as horizontal component of Earth's magnetic field. Right? So, this is already represented over here. Suppose this is the horizontal. This is horizontal. And Earth's magnetic field is directed like this. So as we are aware, the angle which the Earth's total magnetic field makes to the horizontal, that is known as angle of dip. No doubt regarding this. So we can resolve this B into two perpendicular components, one along the horizontal. This component, suppose, is represented by BH. Obviously it will be B cos del. This is the horizontal component of Earth's magnetic field. So we will represent the horizontal component of Earth's magnetic field by BH. While the other one, which is perpendicular to the horizontal component, it is, suppose, BV. It is the vertical component of Earth's magnetic field. Right? So BH, which stands for the horizontal component of Earth's magnetic field, is the component of the intensity of the Earth's total field along the ground. Right? So here also let me represent it. This would be BH, and this one, it should be BV. Clear? So, horizontal component is B cos del. Put this as equation number 1. Vertical component, this one. One is B cos del, the other one would be obviously B sin del. It is B sin del. Del is the angle of depth and B is the intensity of the Earth's total magnetic field. Now let us deal with it mathematically and get the expression for the angle of depth. Right? So if you divide second from first or first from second, what you get is BV divided by BH, it is equal to sine by cos, that will give us tan del. So students, this is the mathematical expression for the angle of depth. So angle of depth is equal to tan inverse BV divided by BH. This is the formula for the angle of depth. Now, regarding the strength of the Earth's total magnetic field, right? For that, what you do is squaring and adding first and second, right? So, squaring and adding, what do you get? BH square. What we are doing is 1 square plus 2 square. So, BH square plus BV square is equal to B square can be taken as common. Over here, it will be cos square del plus sin square del. Obviously, cos square del plus sin square del is 1. So, we are left with B square is equal to BH square plus BV square. Therefore, Earth's total magnetic field in magnitude is given by square root of BH square plus BV square. BH is the horizontal component of Earth's total magnetic field and BV is the vertical component of the Earth's total magnetic field. Clear, students? And here, through this mathematical expression also, we can discuss the very fact that the angle of dip at the equator would be 0 degree, while angle of dip at the poles would be 90 degree. So at the equator, I am talking about magnetic equator. At equator, vertical component of the Earth's field is absent. This is the magnetic equator. Here, the entire magnetic field is horizontal. So, vertical component is not here. So, vertical component is 0. Therefore, use this relationship. Tan del, it will be equal to BV by BH. So, 0 by BH. It would be equal to 0, which implies that del would be equal to 0. Tan 0 is 0. So mathematically also you can easily justify the fact that angle of dip at the equator is 0 degree. While on the other hand, at the poles, magnetic poles, these are the magnetic poles. Here this is the horizontal and this is the Earth's total magnetic field. So the only component of the Earth's field is vertical, horizontal component is absent. So at the poles, BH is 0. Therefore, tan del it would be equal to BV divided by BH. BH is 0. And then divided by 0 is infinity. So, tan 90 is infinity. Therefore, del is equal to 90 degree. So, students, angle of dip at the magnetic poles is 90 degree. So, these are the three physical quantities which are required to specify the Earth's total magnetic field completely. And I would like to mention another technical term which is known as isodynamic lines. Isodynamic lines. Students, again these are the magnetic lines drawn on the magnetic map. So these are the lines which joins or connects those points on the Earth's surface having same value of horizontal component of Earth's magnetic field. Iso means same. So these are the line joining points where the value of horizontal component of Earth's magnetic field is same or constant. So those lines are known as isodynamic lines. Clear? Should I write the definition? Okay. So isodynamic lines are the lines, these are basically the magnetic lines joining points obviously on the Earth's surface where the horizontal component of Earth's magnetic field is constant or same. So that is how isodynamic lines are defined. So let us recap it. In the next 1 minute, let us recap all the three topics definition wise. So students, what I have discussed is magnetic elements of Earth. Like in order to specify the position of an object, the three coordinates are required, is it? X, Y and Z. Similarly, in order to specify or in order to describe the Earth's magnetic field at a place, we require three physical quantities. First one is magnetic declination. Magnetic declination at a place is defined as the angle which the magnetic meridian makes with the geographic meridian. Second one is angle of dip or magnetic inclination. It is the angle which the intensity of Earth's total magnetic field makes with the horizontal. And third one is the horizontal component of Earth's magnetic field. As the term suggests, it is the component of the intensity of Earth's total magnetic field along the ground, along the horizontal. So I hope students you have understood these topics clearly without having any iota of doubt, right? So that's it for this particular session, and in the description section I have pasted a link of my previous lecture. Do refer to that as well, right? So that's it for this particular session. Do join me in my next lecture then. Thank you.